take a look at a projectile. First, let's sketch the path of a projectile. And let's pretend like this projectile is launched from the ground, and we're going to launch it at some angle. Now, that projectile would follow a parabolic path, and then boom, hit the ground again. Now let's list some qualities of this path. Well, some things to note about it is that it is parabolic and it is symmetric. Now it is symmetric in many, many ways. We notice that from the center line, right there, it appears that our shape to go up is the same as our shape to go down. So what our path looks like is symmetric, but we can also extend it to things like the velocity, or sorry, I should say the speed. And I say speed because I don't want to have to worry about direction. Let's say that I launched this marble at maybe 10 meters per second. By the time it goes all the way up and comes back down and hits the ground again, it's also going to be moving at 10 meters per second right before it hits the ground. And that's not just true of when it is launched and lands, that's really true of any corresponding points on either side of our graph. Or sorry, I should say our path. So let's take these 2 points. They are at the same point on the path, however, one of them is on the way up and one of them is on the way down. So let's say our speed now was maybe 3 meters per second. Well, we now would be moving at 3 meters per second at the corresponding point on the other side. So there's a lot of really wonderful symmetry here. Other things to notice is that our total range, maybe delta x, we notice that the range it takes us to get to the peak is half of that. So the delta x of our peak is half as big as our total range. Okay. Now, to start this unit off, we are more specifically going to look at horizontal projectiles. So let's imagine what the path of a horizontal projectile would look like. Let's imagine that again we have another sphere and we're just launching it off of a table. What would that look like? Well, it wouldn't look exactly like what we did before, because before we launched it at an angle. Instead, if we launch it just horizontally, our path would look like the second half of the motion that we just saw. We are only going to see that we are pulled down towards the Earth because of the force of gravity. So really, we're looking at from the peak over from our original path. Now, I'd like to make kind of a little motion map out of this. So I'm going to mark some points. First point I'm going to mark is when we are launched. And just like what we did with motion maps, I'm going to show what the velocity looks like right when we are launched. And since we are being launched horizontally, our velocity is just in the x direction the moment that we come off of the table. Now, after just a little while, so maybe right here, we would expect to see that our horizontal velocity would be exactly the same. And you guys saw this in the lab. So this is the exact same horizontal velocity. But now the force of gravity has been pulling down on us a little bit, and so we start to accelerate down in the y direction, just like how you saw in your lab. So I'm going to add a little down arrow here to show that, yeah, we also are accelerating, or we also start moving down. And if we put these two things together in order to get the total velocity, we see that that total velocity is tangent to our path at that point. And if we do that for any point along the path of a projectile, we're going to find that that's true. So again, our horizontal velocity is always going to stay the same, but the longer that we are feeling the force of gravity and the longer we are in free fall, the larger our vertical velocity down is going to become. So that way, when we add those two velocities together, we see that the total velocity is tangent to the curve. That's pretty interesting for us. Now, the thing to remember is that what happens in the x direction for a projectile is completely independent of what happens in the y dimension. So if we look at this little motion map, we see, okay, our x velocity is always staying the same, but we go from having no y velocity to a slightly larger velocity to a now quite large y velocity by the time we get to the end of our path. So what I'd like to do is I'd like for us to make a Venn diagram of what's going on in the x direction and what's going on in the y direction. So in the x direction, we need to remember that we move at a constant velocity. There are no forces pushing or pulling us in the x direction when we fly through the air, so there's no unbalanced force, and we know that with balanced forces we move at a constant velocity. If we ever needed to use algebra to solve a problem, well, we need to use our constant velocity equation for anything that's happening in the x direction. So we would use delta x equals v delta t anytime we had to think about just what was going on in the x direction for a projectile. In the y dimension, we are going to be in free fall. Okay, so we are going to have acceleration due to gravity in the y direction. And again, if we think about it in terms of forces, when we fly through the air, the force of gravity is acting on us, and that's the only thing acting on us. So that unbalanced force of gravity causes us to accelerate at acceleration due to gravity. So if we ever need to use algebra to solve any kind of a problem, we need to think of all the kinematics equations that we have that involve acceleration. So we're really talking about things like Vf equals a delta t plus vi. We're talking about things like delta x equals vi delta t plus 1/2 a delta t squared. And we're also thinking about maybe Vf squared equals Vi squared plus 2a delta x. Now all of those are familiar to us because those are the three equations that we used back in Unit 3. And because all of them involve acceleration, we could use any of them to help us algebraically solve a problem when we think about a projectile just in the y direction. Now, of course, this is a Venn diagram, so something has to be in the middle. And so if we look at what is in our x circle and what is in our y circle, we want to look for something that is in both circles, but is independent of the direction. So although I see a delta x, I see a displacement in both x and y, but displacement highly depends on what direction you're moving. We care whether we are moving to the right versus moving to the left. There's a big difference between moving right and left. So we need to maybe look for something that is independent of direction. And the only thing that is common between these two circles that is also independent of a direction is time. The time that you move forward when you fly through the air is the same as the time that you move up and down as you fly through the air. So the time that you fly through the air is the thing that can link what is happening to us in the x direction and what is happening to us in the y direction. And that is the only link between these two dimensions.